In this video, I'm going to solve a problem of finding a cycle in a linked list. So the problem statement is that given a head, the head of the linked list determine if the linked list has a cycle in it, and the cycle in a linked list is if there is some node in the list that can be reached again by continuously following the next pointer, right? So here you can see the example 320 minus 4, and you can see minus 4 is linking back to the second node 2, so that's a cycle it's forming. And in the example 1 and 2 you can see that 2 is linked back with 1, so that's a cycle as well. And just a node 1, there is nothing linked with 1 to form a cycle. And the constraints are the number of nodes in the list could be in the range of 0 to 10 to the power 4, which is 10,000 numbers of nodes, and the value of the node could be minus 10 to the power 5 to plus 10 to the power 5. Alright, and the follow-up to the question could be, can you solve it using O of 1 memory? Alright, and this question is frequently asked as well in the big giant tech companies like Microsoft, Amazon, Apple, and Google. Now, solving the problem, I could solve the problem two ways. One is I could use a hash map, right? As I iterate through the list, I can put every node in a hash map. Like I go through 3, put in a map. I go to 2, put in a map. 0, put in a map. -4, put in a map, and it links to 2. And when I see the map, I already see 2 is added to the map. That means I already traversed 2, and I'm coming back at 2 again. That means there is a cycle here. So that's a pretty simple approach. And with that approach, you can see that I will traverse 5 times, right? 3, 2, 0, 4, minus 4, and then 2. So it's almost n plus 1. So its complexity is O of n, time complexity obviously. But for this space complexity, I'm using a hash map. So for each node, I'm putting that in a hash map. That means I'm using extra O of n memory. But you can see as a follow-up, it is asking if you can solve it using constant memory. And for that, I can use a cycle detection algorithm, which is also known as Floer's tortoise and hare algorithm. And basically the idea is that think of a trail, right? Think of a trail where the trail comes back and meets with itself, meaning there is a loop in a trail. If you are walking and somebody else is running in that trail, you'll meet the guy who is running in the trail again, right? Because if it's a loop, the guy has to come back, and it's the same approach. And it uses tortoise and hare. Tortoise moves 1 step at a time, and the hare moves 2 steps at a time, just like walker and runner concept. And at some point they will meet. If they meet, that means there is a loop. Let me give you the example here, right? I have a linked list 7, 8, 9, 10, 11, 12, and you can see 12 is linked back to 7. So now my slow walker and the fast walker both are pointed at 7, like a trail. And slow walker moves to 8, you can see moves to 8, right? And the runner moves 2 steps, so runner is at 9. And the next time walker is at 9, runner is at 11. Okay, keep going. Walker is at node 10, runner is at 7, right? Because it was at 11, so it jumps 12 and goes to 7. Walker moves to 11, runner moves to 9 from 7. Walker moves to 12, runner moves to 11 from 9. Walker moves to 7 from 12, and runner moves to 7 as well from 11. And there you can see that both nodes are equal. That means there is a loop. And that's pretty much how you solve the problem. And for this, you can see that number of iterations in this case is number of nodes plus where the extra, you also have to do extra iteration, because you might not always have your first node as um, as a loop, as a cycle. So you might have to make some extra iterations. And for the space, I'm not using any extra space, so it's constant memory. Alright, now let's write a code for that. So as we said, we'll use Walker as root node and runner as next node. Alright, and I'll keep traversing the trail or the linked list until I hit the end. And the end for the linked list is when the next node is null, right? If the last node has the next as a null, that means I hit the end of the linked list. So if Walker is not null and runner is not null, that means I'll keep traversing. And if I find Walker meets the runner, that means that's a cycle. So I return true, and I'll move my pointer of the walker, right? So my walker now moves to the next step, walker.next, while runner moves runner.next because it moves 2 steps, but runner.next could be null, right? So to prevent that, I will check if runner.next equals to null. That actually means I hit the end of the linked list or trail. That means there is no cycle. Okay, that should be it. It shouldn't get out of the while loop, but just as a fallback, I have to return something, so I'll return false. So let me run the code. Okay, now it passes the test. I have the example 320 minus 4 and the position is 1. That means there's a cycle at first node 2. So this has a cycle, yep. And next one, 1 2, position 0, that means there is a cycle. And in 1 there is no cycle, which is -1. This is the input that I don't need to worry about. And there is no loop or cycle, so I return false. Alright, so let me submit the code, and it says cannot read next. Alright, yeah, I need to add one base case when the head itself is null, right? You can see that head is empty. So if I do head.next on empty, I'll get null pointer exception. So the best case would be if input itself is null, there is no trail itself, it means there is no cycle. Alright, so you can see that it beats 100% of the solutions submitted to LeetCode in the runtime, and memory wise it is using 44 megabytes, 44.36 megabytes, and bits 50%. So that's the solution for finding the cycle in a linked list.